Nice. That sounds like a, yeah, it doesn't feel like the end of the semester. Doing some work on the hammock sounds like a, like a euphemism for taking a long nap. Um, yeah, it doesn't feel like the end. It doesn't feel like the semester. I'm excited for the advanced lab projects. Yeah, I hope you all make them, interesting to yourselves. So good stuff. Let's see who we got here. Missing three people. Nick, Jake, and heard anything about whether summer stuff is still on. Um, uh, I guess which summer stuff are you talking about, Harry? At the college, in the lab. Um, so NREAP was canceled, which is pretty sucky. But you're in the SSEP, so I don't know about that. For me, it's still on the faculty summer fellowships are all in a wait and see, and they promised that they would get us an answer by next week, middle of next week. But of course, they said something like that a week or two ago. Yeah. I don't know if I'm going to be there. I may, to what extent it'll be remote or what. Yeah, it's still up in the air. Blah. And I know a bunch of students in general, like have had internships and stuff canceled. I, yeah. If you have, uh, reach out to folks, reach out to me. We can talk about things. I just wrote back to Nick with some stuff about that, which was basically not a whole lot of help, but yeah, just things to think about. Um, yeah. Um, yeah, I wish I had more. Um, uh, yeah, so here, let's talk about this class. Uh, the way things are looking, we will be working on waves, this definitely through this week and maybe a little bit into next week. We'll talk some about just a little bit about chapter 10, gauge freedoms and stuff like that. Yeah, but there seems to be a lot more online classes. That's a good point. A lot more online classes from the college this summer. So, that's always an opportunity there, particularly for those who still need some of your core curriculum stuff. Lots of possibilities there. Um, you know, it's different, not the same, but an option. Computer science, yeah, all right, yeah, and computer science seems like it's one of those things that was particularly well suited to this kind of thing. So good options, yeah. University of Maryland, somewhat the community colleges. University of Maryland, so both College Park, but also UMGC, yeah. The University of Maryland Global Campus, which used to be UMUC, or University of Maryland Global College, or I don't know what the C is, but yeah, that's their online specific thing. We lost Camille. Um, okay, well, we're recording. Hopefully she'll be able to get back soon. Um, and then there's Jake. So let's talk some more about waves, though. Actually, let's talk about coming up. So homework, I had left out a important piece of information. One of the problems, if so you give you another day on that. If you need more time than that, I don't want you to fall behind and have all your work pile up, but let me know, right? Obviously, we're flexible with things here. That said, right, you don't have to be perfect with it. There's a bunch of extra credit, so do the best you can, and you can still score well with it. Physics T tomorrow, another chance to hang out with. And then I also pushed back the warm up. We're not going to get to chapter 10 stuff until Monday at earliest. So let's hold off on that. So now let's talk actually though about we were talking about electromagnetic waves, um, and we talked first about them inside of dielectrics, insulators. Are we still going to have a homework assignment due next week? Yeah, we actually have there's lots of wave stuff to do, and it's something that it helps to practice and build up your intuition. So homework due next week. We won't. What that does mean though is that I don't think there's going to be any chapter 10 material on uh, any homework assignment, and hence not on the final exam. But yeah, it's the idea there is mostly get you a flavor of it, and it's useful for introducing kind of the some of the ideas that appear in other branches of physics too, in particle physics in particular. Um, so we've been. I'll pause because it seems like we still keep having questions. Okay. Let's talk about our waves. We've been talking about, first we talked about waves just in vacuum. Then we did waves inside of materials, and that had an index of refraction greater than 1, right? And so that the waves traveled more slowly in them. And then I talked about how we can have metamaterials where you can have, for example, an index of refraction that goes negative. And I mentioned having, under certain circumstances with active materials, having an index of refraction that's positive but less than 1 for certain aspects at least. And so now what we're going to do, though, is we're going to move off the real number line, and we're going to get into complex situations, complex index of refraction even. And so what's going to be our connection here, what's going to be the motivation for this is dealing with waves inside of conductors. And so let's see where all this complex behavior is coming from. So we're going to start off again, same starting point, Maxwell's equations, and we'll see, not in detail, but we'll see the wave equation that comes out of them under these modified circumstances. So again, we're going to say no free charge, right? We're just going to have the charge in the, just the charge that's part of the conductor that keeps it neutral, but it's now free to move around. All right, so look out. Maxwell's equations, right? So no free charge in the conductor, so divergence of our electric field is 0. Divergence of our magnetic field, always 0, right? We've got Faraday's law, where the curl of the electric field is given by negative rate of change of our magnetic field. All right, that all looks completely familiar, right? So here's the difference, right? Our Ampere's law, well, first of all, we've got no just free current, but if you have an electric field in a conductor, right, we can get, that can induce a current. That's not the displacement current or anything like that, right? That's just the fact that you've got an electric field creates this current. I'll show where that's coming from right here in a second, but then we still also have our displacement current. Oh, I'm going to actually, let's do this in something where we don't have to have our permittivity, our permeability or our permittivity be the free space values. Let's just leave them more general. Right, so here, let me just add a note where this is coming from, right? Whoops. This is coming from our Ohm's law. We'll get a current arising from the presence of this electric field. All right, and then what we can do, we're not going to do it in detail, but just like we did before. Yeah, which sigma is that? That is the conductivity. That is not the charge density. So we take the curl of each of the fields. Failure of, well, it's true. It's true that we over-define our symbols, right? And it's because we got lots and lots of concepts and a limited number of symbols. I will point out that I can use the word can to refer to this trash can as well, right? It's something that we're used to in language. Did you catch that there? Right? So you pick it up from the context in part. And the difference is, right, this is a, you know, we're constantly pushing you into kind of new areas. So you're always figuring out the context, and it is not entirely familiar context. So you're still learning it. But as you get the can't, great. Um, yeah, that joke was rubbish. Um, the Yeah, as you get more familiar with it, you figure it out from the context and without being quite so uncomfortable. Um, all right. So we got these curls of curls, and we substitute in um, basically the other Maxwell's equations. And doing that, we get new wave equations. We're not going to go through and do it all the way out like we did last time. We know that it can be done. And all right, so we end up with a wave equation that looks like this. Okay, yeah, that looks familiar, right? Second derivative with respect to time, right? That's all the same. Nothing new there, but now we've got this new term because of the mu sigma e that was there. We get a mu, whoops, sigma dE dt. And now and the same thing over here for our magnetic field. These are second derivatives. So now it's not just purely second derivatives in our second order partial differential equation. Now we also have a first derivative present too. And before, right, we had this second derivative, and so if you took the derivative twice and you get back the same thing, that was either an exponential or cosine or a sine. Now we've got something that's not quite like that, right? The only thing where you take the derivative and you get back the same thing is really truly an exponential, but we need an exponential that can give you the same thing and also give when you take the derivative twice and when you do it once. And so just, to highlight these things again, give me a second. Right. Whoop. It's kind of like that. These are our new terms. So, okay, got those. Nice oval. Yeah, it was kind of lousy to start with, but I drew that freehand. No. So anyways, we've got these. The chalkboard, yeah. We still get plane wave solutions. But they're going to be a little bit different. Here, take a look at them and see. So let's do it just now for a wave propagating in the z direction. We know how to generalize that into 3 dimensions. Right, so we're going to write a complex vector. Sorry. complex vector, right? And so we've got complex vector amplitude like before. E to the I, looking much like what we had before, with a little twist on it. What? And here, we'll write out the magnetic field while we're at it. Complex vector with propagation term with a complex twist on it. See, still plane wave solution, but now our wave vector, hence our wave number, if we're specifying this in the z direction, is complex. Right, and specifically, right, when we take the second derivative with respect to space, and then look over at our wave equations on the lower left right there, we can see that we got to have complex wave function squared. It's got to give us u epsilon omega squared. That's the first term, the time term, and plus an I mu sigma omega. That's the second term, which is just a single derivative right there. Okay, so that's our complex number squared. So if we think back to how complex numbers behave, right, we can still take a square root, right? And if we take the square root of this quantity, k tilde squared, right, the modulus of the square root is the square root of the modulus of k tilde squared, but the phase is 1/2 of it, right? Squaring something doubles the phase, so taking the square root halves the phase angle associated with it. I'll write that down in just a second. Pardon me. Right, that's how you take the square root with the complex number. So what we're going to get now is some k tilde like this, right? Which we can actually write, well, if it's a complex number, we can write it as having a real part and an imaginary part. So again, I know my my notation police are going to come after me. Give me 1 second with this. So what I'm going to say is each of those terms, k without the tilde, and this right here is a kappa. So it's kind of like a squiggly capital K. It's for a lowercase kappa, though. Both of those are real numbers, right? So our complex number, k tilde, is built out of a real part plus I times another real part. So this second term is purely imaginary. So we have a real part and an imaginary part to get the overall complex value. Again, that's k and kappa. So I'll put a little. So if you want to typeset it in LaTeX, it's just your plain old \kappa. So, what are those actual values? Well, we can look at them based on our k tilde squared, and they're kind of complicated, and so you can see why we use shortened versions of them. So K, that's a regular K. I don't know why it's squiggled at the end. Right, there's a common factor of omega in it, so you can pull that out. Oh. You seeing why we use a single letter to abbreviate that, stand in for that? And we can do the same, something similar for kappa. Wait, this is looking exactly the same. That's cute. Cute as in horrifying. Look at that. Right? 'Cause we're basically dealing with things that involve, like, we turn it into a difference of perfect squares in complex space. Yeah, big and ugly. So hence the abbreviations with a K and a kappa. Let's talk about what they actually mean, though. So uh, here, actually, rather than trying to cram it in, let me take a picture of this, rewrite one equation, and we'll start over on, not start over, continue on another page. Um, okay. Uh, cool. So I'm going to carry this over to another page. And so again, right, we had, no, like that. And so we wrote out our K and our kappa, and you'll be forced to, you'll be required to memorize those for the next quiz. Just joking. No, you are not at all required. You just know that we've got a complex, the complex wave number has a real and imaginary part, and as needed, we can look those up and plug into them. So then, if when we wrote out, right, in our wave equation, we had a part that had an e to the I k tilde z, right? And so we can expand that out, right? That's e to the I k z, and then I times I gives us a -1. So then we have a kappa and the z distributed like that, right? Oh, and now we've got, like, addition or subtraction in the exponent. So that's the same as multiplying these exponentials, right? E to the minus kappa z times e to the I k z. Right. So then when we go and write out that wave equation, right, not the wave equation, the equation of the wave field, right, we had our complex vector amplitude, right? And then we can take that exponential and separate that out into this exponentially decaying term and then the oscillatory term, right? So we still have up here, oops, in that final exponential, right, we still have This part is still a wavy part. Right? It still has a wavelength, which is 2 pi over that real wave number. And you've got still have a v, which is equal to omega over the real wave number. And then we can write out n is c over v, which is ck over omega, all that stuff, right? That all stayed the same, right? Um, but now the wave's amplitude is decreasing, right? We've got that exponential decay. So what we say is that it's attenuated is another way we talk about that. Right? Attenuated means kind of to make weaker. Right? And when we've got an exponential decay, right, it decays forever and ever and ever. We can still characterize how quickly with z it falls off, right? So we can say, well, when does that kappa z go to 1 so that you get e to the minus 1, which is 1 over e, over your original amplitude? Well, that happens when at some distance, z equals, let's call it d. And so when kappa times d is equal to 1, so d is going to be 1 over kappa. And so this is called the skin depth. Right? We can make a plot of what's going on here in terms of what the electric field, just the real part of the electric field. So here, let's make this E like that. At some point in time, it's a function of Z, right? And it's oscillating. And we did exactly a function like this, right, in our practice with complex values. Okay? Right, so it's decaying downwards like that. So I can even, right, draw out kind of the envelope of these things. Three dot triangle. Where, where? Oh, the 3 dot equals, oh no, that's not a 3 dot triangle. Yeah, that's supposed to be an ellipsis, 3 dots in a line. I don't know why 3 dots, just because we could just say it. Here, I'll fix that. How about this? Yeah. In other places, the 3 dot triangle means therefore, but yeah. I didn't mean, that was my inability to make dots in a straight line, at least in this medium, right? And so when does this reach? I'm going color crazy now. So this is E, our original value, over lowercase e, right? It is a little bit more than a third, kind of right there. So where those hit, somewhere around here, that's going to be our D, skin depth. Right? So it's a measure of, again, like how far this wave will travel before it gets attenuated by a certain amount. And we can see that, oh, we can't see, but if you remember back, our kappa depended on epsilon, on mu, on sigma, and also on the frequency, on omega. So all those things go into there. What else do we have to look at? Let's write down some more properties here. We still got to have a transverse field. Actually, both E and B are transverse. Cool. So since we have, let's just make our life simple. So let's choose the direction of the electric field. We'll call that X. We're free to do that because we just have this thing going Z through this conductor. Nothing else is going on. Once we start talking about hitting an interface between two different materials, then things get more complicated, and we don't have complete freedom to choose to name our directions. So okay, let's write this thing out and see what this tells us about our different fields. So here's, again, that's supposed to be a tilde. All right, and so now let's separate out the amplitude, complex amplitude, from the polarization, though. So the vector part of that, I'm going to separate out. We often write the vector part at the end, so I'll do that, but just know that that's really coming out of the E naught vector tilde. All right, so we got the decaying part, the oscillator part, and then polarized in the X direction, right? And so that we still have, right, that E naught tilde, right, is still equal to E, our real amplitude, times E to the I delta, with that phase constant, E to the I delta, but we've folded that into there. So let's see what this tells us then. So then we can take the curl of the electric field. We can take Faraday's law. All right, so we get a magnetic field here. All right, so when we take the curl, we're going to get a K tilde. And then on the other side, when we take the time derivative, we're going to get an omega. So when we move it over, we get this. You still have your E naught tilde, and then an E to the minus, kappa, our decaying term, Z, and our oscillatory term. And again, because of that curl, though, we're going to get this field in the y-hat direction. So just put a note right there, right? It is still perpendicular to our electric field, and also perpendicular to our wave vector, like that. So a couple things though, right? So, but now we're multiplying. One thing that's different here though is we're not just multiplying by the real wave vector, we're multiplying by the complex wave vector. So to understand that, let's do something here. Let's write this. Here's another, thing where the notation, they're different choices we could make with the notation. Let's write K tilde. I can't call the real part of it just a plain K without the tilde, because we've already, plain K is sorry, we can't call the modulus that, because that's we've used that for the real part. Oh, sorry, I should shut up and just write for a second. So for the modulus, we're going to use capital K. That's not a kappa, that's a capital K. And then e to the I phi. Right, so here, let's write this way. So if this right here is K, right, and this is the real part, here's the imaginary part, then that right there is our capital K. That right there, this is the imaginary part, so this is kappa right there, and then this is the real part, so that is plain old K. And again, just as a reminder, right, we just defined our capital K is equal to the modulus K tilde, right? And you go back and you look at that, and that is, right, how do you get the modulus of something? You take the square root of the square of the real part and the imaginary part. And you go back and look at those and stick in the values, and that turns out to be a bunch of that stuff cancels out. Lowercase words describe variables. I missed some of that, but yeah, I mean, what you need is better notation or something like that. It's trying to reuse the alphabet. Yeah, I don't know. Like there are, and the problem is there are competing conventions. So it's hard. There isn't any unified convention. I'm sticking with Griffith's convention so as not to make things worse. That's under a square root. So basically, yeah, there we go. The minus one parts. Minus one and plus one have canceled out. That's what's happened right there. Oh, and so this is purely real, right? Because it's the modulus. And then that phase angle, phi, right, is just going to be the inverse tangent of the vertical component, so that's the imaginary component, kappa, divided by the horizontal component, the real component, k. Right. And so what we've done then is, if we write this whole thing out, let's write the whole darn thing. So our complex vector function for the magnetic field, right, is equal to K tilde, but let's just take the real part of that. So capital K over omega, electric field amplitude, and let's just take the real part of that, and we'll take the phase factor and write it out explicitly, because by multiplying by a complex number, we have an additional phase to out. All right, exponential decay, and then e to the I, we have k z minus omega t plus delta, right? But this is the delta from the electric field, right? So I'm going to actually label that delta sub E up there. So I'm going to put a little sub E up there. Oh, that's horrible. Little sub E, to show that it's not just generically phase factor, it's specifically the phase on the electric field. And then by multiplying by that complex number, we multiply by e to the I phi. So that's the same as adding another I phi in the exponent. Oh, and all this along the y hat direction, though. So what, again, let's just highlight this bit right here. Oh, that's not what I wanted. That there. So what that means is we've added a phase delay. All right. And we also have another relationship. We also, the real amplitudes so B naught isn't just equal to your real wave number. It is this capital K, which captures both the real and the imaginary parts added in quadrature. So again, as compared to oh, that was an omega. I'll fix that we're pointing at. Yeah, that's pretty ugly. Cool. So different kind of behavior. Right here, different relationship with our amplitude. So this right here is supposed to be an omega there. A little bit better. So we've got this phase lag due to the fact that we're basically stirring up this current inside the inside the conductor. And we can think of it as you get this current flowing, and you also have the oscillating electric field causing the yeah. So basically that adds this extra phase delay in terms of like as the current oscillates back and forth, it re-radiates electric field, and that's delayed. Here. Okay. So we can use this complex wave number to describe our the attenuation of the wave itself, right? The fact that the wave decays away exponentially. Let's take a look now at an interface, and specifically, right, because we know the wave is attenuated in the conductor. We're not going to go have it going from one conductor into another because it can't come from far away in one conductor because it'll die off. It has to come from far away in, say, a non-conductor and then go into a conductor. So here, let's take a look at an interface. And here's one material. and then we'll take another material over here, and we'll call this material 1, this material 2, and let's make this one non-conducting, and let's make this one right here conducting. Here, really, so just like before. Equations, that's equations. And we're going to apply the boundary conditions. Right? And again, the point of this right here is to show you this general technique that we've got. We know the general form of solutions, but we want to find the specific form for this situation, and the specific form is dictated by the boundary conditions. But also, yeah, this is just a very common behavior to have waves traveling through one kind of material, like air, and then hitting a surface. And so what happens then? We're not going to go through every single variation. We're just going to do this for normal incidents. So let's write out the boundary conditions first, the boundary conditions right here. So we've got the field perpendicular, the electric field perpendicular to the surface, and we can just treat that surface as a plane, and the difference in the field, and really it's our D that's generating this, our electric displacement. But if we're dealing with linear dielectrics, we would get this right here. But we're saying there's no free charge present. There's not just charge sitting there. The only charge that we were talking about is charge that gets pushed around by the fields. So that's just going to be equal to 0. Just like before, right? You don't get any magnetic field discontinuity for the perpendicular component. All right. No discontinuity in the parallel electric field component. Again, because Gauss's law tells you about if there's charge at that interface, you get field pointing away from it. All right. And then finally, there is a discontinuity in our magnetic fields. And I'm writing the parallel component still as vectors because there are two directions still that are parallel to the interface. Right? And this would be given by any current that we had. So this is not the same K. This right here is in fact the current density. Sigma up above was the charge density, not the conductivity. Notation, right? But again, no free charge present, so that whole thing's just 0, right? So we've got these, and now what we do is we know the general form of our wave equations. So we know that there is a field coming in, incident, there's a reflected field, and there's a transmitted field. So let's write them all out again. Everyone, yeah. So are you getting a theme, right? So I know it's a bit repetitive, but again, this is a technique. You can use this technique for every kind of interface in E&M. You can use this technique. Actually, a lot of these ideas, the same technique for any kind of separation of variables problem. You can use this technique for scattering in quantum mechanics off of a change in your potential. So really, really useful technique, right? So three components. We've got the incident component. Is this kind of the case for solar panels? I mean, you have, yeah, so I mean, for all kinds of things, for solar panels, for the Earth, you're looking at like greenhouse warming, right? You have to think about the component of the radiation that's incident, the component that's reflected, and instead of it being transmitted into the bulk of the Earth, or usually transmitted into the bulk of the solar panel, you're often interested in the absorption instead. Right, so that's just in general. So here for the solar panels, yeah, the wave gets turned into. It turns out it's not exactly just a conductor, though, right? The solar panels are a semiconductor, so it's a little bit more involved. But yeah, it's a you can you can use the same initial set of techniques, though. And this is so just do normal incidence. So this is traveling in the z direction like this. So we can write this with an incident amplitude, e to the I, and then outside, right, we're going to call it just K1. That's a lowercase. I'm sorry. It's supposed to be a lowercase k. Because it's in material 1. Z. And that's in the x hat direction, right? And then we've got our incident magnetic field, which we can relate. And that's just going to be 1 over V1 times that same amplitude, e to the I, same oscillatory term, right? It's purely real wave number, so there's no phase change or anything like that. It just is pointing perpendicular, so in the y direction. And then there's a reflected wave. So reflected complex vector function. It's got its own amplitude, and it's got the same wave number, but it's traveling back to the left. So the wave vector is opposite in direction, so opposite in sign, since we're just one-dimensional. And then our magnetic field, that's an R. Okay, so there's a 1 over V1, but our V is actually negative, so it's the same speed, but opposite direction. So there's a minus sign, or another way to say this, so we need that minus sign just to preserve the correct relationship that E cross B points in the same direction as K hat. It's got the reflected amplitude still, E. So again, that's a minus K1Z. Okay. And then that looks the same. Yeah, all the same. What's different right now is what happens with our transmitted wave, right? Because now the transmitted medium, the medium into which we transmit, is now a conductor. Everything else was the same leading up to this, though. All right, so let's write these out. Vector complex function. Okay, it's got a complex amplitude, like always. That's looking the same, except with the addition of the fact that this is a complex wave vector, right? It's got the imaginary part, which leads to that attenuation, that exponential decay, and it's got the the real part, which continues to give you the oscillatory behavior. And then the wave, the magnetic field wave. Right, so now this is K2 tilde, right? So there's going to be a phase shift. To tilde. See. All right. So we've set it up. Now what we have to do is we've got all these things, and now it's just apply these boundary conditions successively. Right. So again, same overall technique, same pattern that we were using before. Right? Write down the general form of our waves, and then use the boundary conditions to nail down the specific relationship between all these coefficients. Uh, right. So I wish I had like a board that was twice as wide so we could keep these things and refer back to them as we apply the boundary conditions. But I think what I just had to do is make them all disappear. And we're going to apply these boundary conditions. The very first one, though, here, let's see what we're going to do to start with before we lose these. We're going to apply this very first boundary condition right here, right? Because our electric field, all of them are parallel to that interface in the x-hat direction. So this is going to be the useful one to start off with right here. All right, so let's go ahead and do that. And if we do it, we can factor out the e to the I omega, e to the minus I omega t from every single piece there. And we're applying this at the boundary where z equals 0, so that the entire exponential actually goes away. And what we're left with then is just a relationship among the amplitudes. Right? Because it's all in the x-hat direction too, so we don't have to worry about their vector nature either. All right, so that's one piece of information. Hold on to that for now. We've got the one that has to do, so the perpendicular components aren't going to tell us anything because both our magnetic field and our electric field are pointing purely parallel to the interface. So here, I'll just actually make a note up front. BC1 and 2. Right, there's no perpendicular components for either field. So we're left with just the two boundary conditions that tell us about the parallel components of the field. And so that's the electric field. And then for the magnetic field, we can factor, same thing, the exponentials are all going to drop out. We can factor out the, we can rewrite the magnetic field amplitudes as 1 over v times the electric field amplitudes. So write this as u1 v1, but there was a minus sign for the reflected, right? It was minus 1 over v1 for the reflected field. And then minus inside here, this one became, it was K2 over omega. We can't just write it as 1 over V. All right, so this is the part, again, where things are getting particularly different, right? Oh, and all that was equal to 0, because I basically moved that over to the other side. Oh, no, I'm sorry, the change was equal to 0. All right, so let's take this one right here. I'm going to clean this up. Let's rewrite this. So actually, let's give these a name. No, I don't know. All right, we can rewrite this as here, E naught I. I'm right under where that was before, E naught R. We're going to move the next term over to the right, and we're going to move the multiply through by mu1 V1. And so then I can write this right here. It's beta, but it's a complex beta now. So we're doing the same thing we did when we had two dielectrics, but now things are complex. Right? It's mu1 V1, and it would be mu2 V2, but a V2, we've got an omega over K tilde. So this is omega times K tilde in material 2. All right, so the exact same techniques are going to work for us, but again, we're still dealing with complex functions. So, all right, we've got here that one and that one. These two equations form a system of equations. So let's solve for the reflected amplitude with phase, right? And the transmitted amplitude with phase, right? And it's going to be in terms of the incident amplitude, right? Omega V. And now the other thing that goes into there, I'm sorry, mu V, the different permeabilities, the different speeds, but now the frequency plays a role too. We're not just able to combine K and omega to give us in terms of the speed, right? Because we've got this complex wave vector, we really still have to keep track of it separately. Right? So it depends on your incident amplitude, the properties of the materials, but also the frequency. So it's going to become frequency dependent. Right? And even like, right, the things like the skin depth that we wrote before, right, that had omega in it. It was frequency dependent. So yeah, exactly. Different frequencies will penetrate different amounts. You'll get different transmission and so on. So here, let's write these things out. It looks the same as our solutions before because we have the exact same system of equations, except now we've got a complex beta. Right? And that's the nice thing about doing this with complex numbers, right? Is we can just say, oh, hey, look, it's the exact same thing. Right? If we had done the real and imaginary parts written out separately, it wouldn't have really looked the same. So it's related to stuff like that. Yeah, indeed. It's actually not exactly. Yeah, I need to stop and think about that for a second, though, because I think it's actually just you. Yeah, you're very opaque. I think the lower frequency stuff will penetrate deeper in general. But I'd have to stop and pause. Yes, Right, and this is even like, so we'll talk about this, and we're out of time. I just want to try to get kind of tie this off, but then we'll talk about what this means physically, right? Because this is a whole bunch of math right now, but we want to understand what does this mean in terms of like our bodies, our microwave ovens, hey, our um, just real world phenomena, right? What is the physical meaning of all that? And I think I may run out of time for that, and we may have to wrap that over to the next class. Let's see. Uh, yes. Yeah. So what we're talking about there was something a little bit different than with X-rays. Sorry. Du- du- du. All right. Again. Right. Yeah. So things like how well does base propagate through materials, through interfaces, stuff like that. Indeed, absolutely related to these kinds of questions. Uh, uh-huh. Indeed. No, it's that academics help with understanding parties. So it's and also like traveling around corners and stuff like that. But it's also going like how well they transmit and get and rather than getting attenuated. Bu- 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 bu. Um, let's write down a couple of these things right here. Okay. Yes. Mm, mm, mm. Here, right? So I want to see a couple things. Let's just understand a couple things about what's going on. So yeah, just right equals right k tilde equals k plus I times kappa, like that, right? Um, you get 0.1% extra credit, but you have to bear the consequences. So k or kappa, totally worth it. I don't know. Remember, you got to live at close quarters with these people. So when I say K or kappa, there's gonna be one thing that's different for the two of them, but I'm writing a single. Uh, bu- 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 that's squared, and here we'll do plus or minus 1 all to the 1/2. So here, let's do it this way. Let's make um, uh, K be the red plus and the green. Do you see what I'm doing right here? My kappa is going to be the minus. Right. Um, so, all right, let's take a look. What happens if you got a perfect conductor? Which does that affect? Does that affect omega? No. Does it affect epsilon? No. Does it affect mu? No. It affects sigma, right? Sigma um, equals goes to whatever, infinity, right? So then, right, this whole thing, the whole darn expression goes to infinity. So K and kappa and hence. Oh, are you watching them on YouTube or where are you watching them? Yeah, because if you watch it on um, Blackboard, you can see the chat, but you can't change the speed, and it doesn't have the closed captioning. Right, so if sigma goes to infinity, yes. So if you go to the section called links, not links, called notes on Blackboard, um, then you can, then I have the screenshots that I'm pausing to take each time, but I also have links to the YouTube. Right? And so you can watch it at accelerated speed and with closed captioning. It does a pretty good job, surprisingly, but you don't see the comments. So you see me like kind of responding, suddenly stopping and going off on a tangent like I just did there, right? So anyway, so these things, let me just, I wanted to finish up second or two, not second, last 2 minutes, because I got distracted, right? So if sigma is infinite, double time speed, then both k and kappa go to infinity. That means that your whole k tilde goes to infinity. And so what then that means, right, remember beta is proportional to k tilde. So our beta, and these are complex infinities, but it doesn't matter. It's infinite, right? So that's what happens. So then what happens, you get E naught R, right, is equal to minus infinity over plus infinity. So that's just going to give you a -1. Totally okay, because it's this exact same expression, right? You can do L'Hopital's rule if you're like uncomfortable with ratios of infinities, right? So you just get that right there. Oh, and what happens to the transmitted in amplitude? Well, you get 2 over infinity, so that's 0, right? So for your perfect conductor, you get perfect reflection with 180-degree phase shift. Right, and so that's like having, right, a string attached to a clamped point, and you make a wave on the string. That's E naught tilde I. Yeah, the minus sign came from, where did that minus sign come from? It came from over here, right?
Get EOT equals 0, but not -1.
Yes, because you've got 1 minus infinity over 1 plus infinity, which is the same as negative infinity over plus infinity. But it's the same beta, right? It's minus beta over positive beta. So that just gives you overall a -1 over here. That's where that minus sign is coming from. Is that good?
Thanks.
Right, like a wave hitting a clamped string, right? Because at the perfect conductor, you have to have E equals 0. Right? So you can no longer have any wave there. And so just like, right, when you have a string that's clamped at the end, you send a wave down, you get perfect reflection, but with a 180-degree phase shift. Oh, and perfect reflection, right? What does that mean? Our conductors are shiny, right? Shiny metals. And if you know a metal that's not shiny, it's usually because there's an oxidized layer at the surface. So it's not a perfect conductor at the surface. So we'll have to spend a little bit of time and look into like our sound waves and stuff going through walls or and so on, that kind of transmission. But what we have learned to understand right here is that why are conductors shiny? right? Because of these equations right here, we see that we cannot have any transmission in, so all the light that strikes it has to reflect off of it. Woo! And I went over yet again. But that's all I have. We're going to talk about different kinds of speeds. What happens when speeds are different for different frequencies in our next class. And maybe lump in some of this complex stuff too. See what's going on. Good stuff. I'm going to screenshot this and I'll talk to Camille, but everyone else, I will see you on Friday. Let me know if you still have questions on the homework though. Take care. Yeah, see you all.
Dr. Grossman.
Yeah, here, give me 1 second to finish taking the screenshot. Otherwise, I will forget and not get it to you. All right, save. Cool. Okay. Yes. What's up, Camille?
I won't be in class on Friday because I checked my schedule for work and they scheduled me outside of my availability. So
Okay. Yeah, I'm sorry about that. Would it be okay? Do you want to take a second in your, because you're in a different window from Blackboard itself. Do you want to take a look and see where the notes are available right now?
yeah, it's
And
under class notes.
let's see. Yep, class notes, and you can see the whole list of them then going down. Um,
Yep, I see them.
Cool. And so, yeah, the recordings will be up on YouTube, or you can watch them through Blackboard. Um, yeah, whichever you prefer. So aside from me kind of out of nowhere stopping and changing topic because someone makes a comment that you can't see if you're watching on YouTube, I think it probably is the better experience. So that's the first part, right? Making up that way. The second part is you can ask me questions, right?
Okay.
Is that so? We're going to be taking a look. Yeah, it's actually going to take the whole class. Taking a look at what happens when you've got materials where the index of refraction isn't the same. So the speed of the wave isn't the same for all frequencies. And so we'll talk about like, well, what does it mean to have different kinds of speeds? What speed do you use to characterize it? Things like that. It's mostly related to stuff that's in the book. I've been sticking relatively close to the book, just again to avoid added confusion. But I do want to make sure, like, I'm available if things aren't making sense. You can even like say, what were you talking about at minute 27 in when you said this? Like, you can get that specific, or just say, hey, that whole people kept interrupting and I didn't understand what was going on when you were talking about the electron oscillators or something like that.
Okay.
And anything that helps, yeah.
I have another question.
Sure.
So I'm doing research experience with Dr. Billitson, I guess starting May 26th, and Dr. Dupree said I need to talk to you about signing up for, I think, Physics 352. I'm not sure the course number.
It's gonna be It's gonna be Physics 350. So I have a couple questions for you related to that. You're doing the applied physics concentration, is that right?
Yes.
Okay, cool. So yeah, you do need to do that then. And so right, so you can if you don't mind, send me an email, and I will copy you on the email I send to the registrar to sign you up for it. It is a 0 credit class, so there's no tuition associated with it. Because if you take a class during the summer, that's not covered by normal tuition. You have to pay for the credits, but this is 0 credit, so you have to pay $0. It's pass fail. You will pass once you've done your end of your, like, when we come back, and I really hope we're coming back, but whenever when we resume in the fall, we will ask you to give some presentation about your summer work to other students. As your main audience, the faculty will be there too. And so that completes the Physics 350 then, your
Okay.
research experience. But yeah, just send me an email as a reminder, because I'm going to get off of here. I'm going to see that I have 20 emails, and I'm going to start responding to them. I'll forget this one.
Okay. I'll send you an email. Thank you.
All right. Yeah, cool. I'm glad that you folks are able to keep it going, that you're able to do it, even if it's remotely.
Yeah, I felt like really lucky because a lot of the internships I applied for were canceled
Yeah.
due to
Yeah.
like circumstances.
Yeah, a whole bunch of, even some of the people in this class and in E&M have had their internships canceled. So it's, yeah, I'm glad that you folks are able to go forward. But that's the nice thing about doing kind of data intensive stuff, so you can
Yeah,
do it
it's
remotely.
mainly going to be data analysis.
Yeah. Yeah. No, good stuff. Cool.
All right.
Um,
I guess I'll see you Monday? Yeah, Monday.
okay. Will you be there tomorrow, or are you not available
Oh
tomorrow?
yeah, tomorrow. I guess I'll see you tomorrow.
And we expect that one to be pretty short. Just everyone kind of checking in. Is what I thought about, kind of thing.
Okay. Thank
Cool.
you.
All right. See you then. Take care.